is when it's,
Say that again.
1 is when we have to be at, right?
We have it till 1:30.
Well, I definitely won't go that long.
Welcome to the October meeting of the Salt Lake R user group. I imagine most of you have found us through the meetup group online, but if you are not part of our group there, please find us there and join so that we're having meetings, what we're going to be talking about, and stay connected there. Today, I'm very...
And subscribe to the YouTube channel.
And you can subscribe to the YouTube channel, because I think if we get enough people subscribed, then we get to have our own URL instead of a terrible string of nonsense characters. So, if you all subscribe, we can change it to something meaningful, which is then easier to share. So, today, here in October, we are going to be learning about Bayesian Additive Regression Trees, which I'm very excited about. This is something that's new to me, I've not used, so that'll be exciting. And Nathan Barton is going to be sharing with us. Also today, we are unveiling the brand new hex stickers for our user group. I'm pretty excited about this. A little bit of a hex sticker junkie myself. My laptop, which is not here today, is in fact covered with our package hex stickers. So if you come to one of our meetings, you too, which you all have, you too can have one of our Salt Lake our user group hex stickers. And this hex sticker was entirely in R. So the whole thing was made with R. It uses census data. So there's a map of Utah on it, and it uses census data, and R packages, mainly tidyverse packages, were used to make this whole sticker. So come get one from one of us up here if you would like to. So Nathan is going to be sharing with us, and then afterwards we'll just announce about what we're doing next month and anything like that. So thank you so much, Nathan.
Yeah, thank you. Thanks, everybody. It's great to be with you today. So I wanted to talk a little bit about Bayesian additive regression trees, and just to kind of, I guess, give you an idea of where we'll go. I don't know how many of you are familiar with Bayesian approaches or with boosted tree models, regression tree models. So I kind of wanted to keep this fairly high level and then give you a fairly simple application example. It's very easy to implement this in R, and there's a really useful vignette as well that you can look up afterward. If you have questions as I go, feel free to raise your hand and ask, or at the end, there should be plenty of time for questions after. But what I wanted to talk about is why sort of the driver behind Bayesian additive regression trees, at least in the work that I do. A brief overview of boosting in regression trees, because that's sort of some of the fundamental principles behind Bayesian additive regression trees. And then dive into BART directly, and then show you that application. So first, as I'm sure many of you here know, whenever we're talking about something we want to use BART with, it's always in the realm of prediction. BART is not good at telling you causal relationships between predictor variables and your outcome. There's a little bit that you can get from that, similar to what you would see in other machine learning algorithms, but BART is all about prediction. And so kind of some background and some math here with classification trees and boosted models. You kind of start off with a function, a data generating model, where you have a function of some inputs plus some error giving you your output that you're interested in predicting. And so we can think about this in terms of regression trees. And without getting too into it, this is kind of a helpful picture, I think, around additive regression trees. So you have data and these inputs, and at each of these nodes there is a splitting rule where some of the data goes to one side and another data goes to the other until you get sort of these smaller prediction spaces. And you add those prediction spaces up to get a better picture of your overall prediction space. And so this is another image to kind of think about it, where you have a bunch of weak learners adding them together to get a clear picture of the whole. So you've got this picture in the on the left-hand side of the screen here, which represents the data that you're trying to look at. And then you run your algorithm through it, and through one iteration, you can kind of see how the colors aren't very predictive yet, but as you run it over many iterations and build all of those smaller weak learners and add them together, the prediction in the bottom right, or the picture in the bottom right, starts to look a little bit more like the picture at the top. So that's kind of what is meant by the additive regression trees portion, is you're taking each small part from the regression tree that outputs a relatively weak learner by itself, and then combining them together to get this bigger picture of the whole. And so one of the main problems with this kind of approach is overfitting to the data that you're training on. And this is where the Bayesian approach kind of penalizes against that to prevent overfitting. So just a quick review of Bayesian statistics and Bayes' theorem. So, and this applies to the Bayesian additive regression tree approach. You start with a prior distribution assumption and the likelihood function from your data. And then from there, you get a posterior distribution that you can sample from, which is this P, A given B. And so in the Bayesian additive regression tree approach, we have the prior assumption, and the prior consists of this big ugly right here. And the prior is put onto the tree structure and to the leaf parameter of the regression tree. You can run BART in both a continuous outcome scenario as well as a binary classification outcome right now. There was a new package that was released. I don't know if it does multinomial outcomes, but in the case that you do run it on a classification problem, it kind of changes a little bit of the assumptions in your prior. But what this regularization prior on the parameters for your regression tree does is it prevents that overfitting. And I'm going to skip forward to this one for a minute. This was sort of the best picture that I could find to kind of describe how the regularization prior prevents overfitting. So the idea is you've got water and that represents your data. And the basins here represent your regression tree. So as the data flows from one basin to the next, some of the water is captured, or some of the data is explained by that basin. And then the rest of it, the residual, flows to the next one, on and down. You finish your tree. And the rest is just that error term in the final basin. And what the regularization prior is doing here, and what the Bayesian assumption is doing, is changing sort of that shape of the basin to either capture more or less of the data. And it balances it as it goes down to prevent overfitting relative to a training data set. So it's not a perfect picture, but that was sort of the best picture I could find on Google, at least in the way that helped me understand what was going on. But so the tree structure, those basins, and how the water trickles from one to the next, it has a bunch of these splitting rules where an observation moves to a different node depending on whether the splitting rule is satisfied until it reaches a terminal node. And the other thing I guess to point out here is if you do run a classification model in Bayesian additive regression trees, it assumes a probit model instead of a logit model. I don't know why they picked probit, but maybe they were economists. So this is just an example of how well BART functions relative to some other machine learning algorithms. So the original developers of this approach, in their paper that they published, compared BART to random forest neural networks and boosting algorithms. And what this is showing is the relative root means, or root squared mean error. Am I saying that right? Which is the mean error divided by the minimum root squared mean error for all of the different models that they ran. And they had 42 different data sets for this. And they sampled from those 42 different data sets to create about 850 test and train data sets that they then ran through each of the different approaches. And the idea is you want to have a smaller relative root square mean error. And the top one is just the default Bayesian additive regression tree approach with no real tuning and no cross-validation. The one underneath it is Bayesian additive regression trees with a little bit more tuning done and some cross-validation. So you can see how the performance improves fairly significantly when you add that in. And you can see that it outperforms all of the other algorithms when taken across the entire realm of all the data sets. So it's pretty powerful. And the good news is it's pretty simple to use in R. So there is a package in R called BART machine. There are a few other packages as well that do this. Bayes tree is one. That was the first package that was developed by the original authors. It runs very slowly. BART machine, they wrote it off of, I think, a Java platform, so it performs much faster than the original Bayes tree. And then, apparently in August of 2018, I just discovered this putting my slides together, a new package was released called BART. I haven't had a chance to play much with it, but it actually looked pretty promising. So if you want to try this out, I would recommend maybe comparing the two. But the BART machine package comes with a lot of really nice functions that allow you to easily check your assumptions, to sort of visualize the data. There is some ability with the package to look at how important each of your predictor variables are. I should put importance in quotation marks. As well as looking at things like partial dependence. Like I said, there's a really good vignette that kind of steps through all of the different functions. But it also allows you to really check the MCMC, convergence diagnostics, that kind of stuff, which I'll show you some of that. You can estimate prediction intervals very easily, unlike some other machine learning algorithm packages. You don't have to do a whole lot. And we'll kind of dive in now, I guess, to sort of an example here. So I work at Intermountain Healthcare, and one of the things that we were interested in doing is predicting length of stay for patients who are readmitted to the hospital, and wanting to know just kind of if somebody is readmitted, how long do we expect them to stay, so we can think about that in terms of cost and in terms of their experience. So I also, a little bit of background, I'm an analyst here in the Office of Patient Experience. So we looked at CMS readmission cohort patients at all Intermountain Healthcare hospitals from 2015 forward for this. The training data set was 2015 and 2016, and then the test data set was from 2017 forward. This analysis is old, so I believe that ended the first part of 2018. In order to be included in this, the patients for their initial stay had to have been in the hospital for at least 24 hours. And then some of the variables that we included in this were age, readmission, type, whether they were pneumonia readmission, a acute myocardial infarction readmission, so heart attack, for those of you who may not be familiar with healthcare, stroke, COPD, and I'm forgetting another one, total hip, total knee replacement surgery. So if you came in and had one of those and then were readmitted within 30 days, we wanted to know how long did you stay. We used age, like I said, readmission cohort, like we talked about, the Charlson Comorbidity Index, their median income value, the index severity of illness, so from their first encounter, when they left, how was that encounter rated in terms of how sick were they? Their discharge disposition, so we wanted to know if they were discharged to like a skilled nursing facility or to some other place, hospice would be especially relevant. And then if they had an infection during their initial stay, because that often leads somebody to have to come back to get treatment. And so looking at the distribution of the outcome, one of the assumptions with BART is just regular normal OLS. And so we need normality in our errors. And so just interested in how the length of stay breaks out, you can see that it's pretty log normal. And so anticipating needing to make a log transformation here. So we run, this is the code to run BART machine inside of R. It's pretty simple. X is a matrix with all of your predictor variables, and Y is a vector with your outcome. So the verbose means I don't want it to print out a lot of stuff. And then the serialize equals true is the parameter you set if you want to save the machine output to use later, to load it back in. And then looking at the output, this is sort of the default output from BART. It gives you some very simple statistics. And one of the things that it does for you right off the bat is it shows the normality of your residuals to see if that assumption is met. As you can see in this case, it is not. The test is significant. So I guess we'll get to the log transform. I just want to show you as well the convergence diagnostic. So this is the function you call to look at the Bayesian conversion diagnostics, convergence. And you can see here, there's nothing very alarming in these. I wish I had a good picture of something that was alarming, but it gives you these 4 plots to be able to compare to. And then running the same thing just now with the log transformation on length of stay. And looking at the output, you can see down here that the test is no longer significant, so we've addressed that assumption and can move on. One thing I don't have in here, but you can change the number of trees, the burn-in period, and the posterior samples. There are arguments in the call to BART machine. I just went with the default. More often than not, that's sufficient. But if you're having weirdness in your convergence diagnostics, you might need to tweak that. So again, looking at the convergence, nothing too exciting here. So this is looking at the prediction now on the training data. And then I just, for fun, compared it to OLS. It doesn't make a lot of sense here because OLS will always be fit perfect in terms of the average, because that's what OLS does. You can see BART doesn't line it up perfectly. And a lot of that has to do with the regularization prior assumption that we put on it. And so where this gets interesting, and I guess here's a comparison of the root mean squared error. So you can see they're pretty close. OLS is a little better. But where this gets interesting now is on our test data. So not much changed in the prediction from the BART model. It's pretty close. If I go back and forth, you can see this one is a little bit closer than this one, but those lines are pretty darn close, and now OLS is all over the place. And you can see the root mean squared error now for BART is much better than it was for OLS. So if we wanted to now calculate a prediction interval from this data, it's pretty easy to do that as well. So the function you call is just calculate prediction intervals. This is that's the BART machine object that I ran and stored using the log of the outcome. Patient X is a patient who, I just made this up, is 30 years old, was in the hospital with an acute myocardial infarction, had a Charlson comorbidity of 17, so very bad, very sick patient, a median income of $30,000, also a very poor patient, and an index severity of illness of 4. Initially discharged to a skilled nursing facility, who also had an infection. So this is kind of based on social determinants of health and the health status of the patient, someone who's very sick. And in this case, a 95% prediction interval for how long we would expect the patient to stay is 1.3 to 10.1 0.1 days. Pretty wide range for that specific case. But you could substitute that in, instead of patient X in this case, which is just one patient, you can plug that into a data frame or a matrix to be able to get the predictions for all of the different patients. So it works very similarly to using any sort of a linear model prediction type approach to get the output. So, but in a very, like I said, very high level overview of how it works, how we use it, or how I've used it, I guess, in this specific case. But are there any questions? Yeah, in the back. Do I need to repeat these? Or
I guess several ones. Can we go back to the slide with the normality test, the Shapiro-Wilk test?
Sure.
Because I was a bit confused as to what we were saying there. Now, the Shapiro-Wilk test, the null hypothesis is that the data is distributed normally, correct?
Correct.
So in this case, our p-value of okay. So this is saying that it's not rejecting that, right?
Correct.
Okay.
But the first one, which is probably what you're referring to,
Yeah, that's what I was wondering about. Yeah.
is significant. And again, that's means we needed to do the log transformation.
So that was
on the outcome.
pre-transform
That was pre-transform.
Okay,
Yep.
I guess the second question on that point was, according to the model construction, errors have to be normal. Does the data itself have to be normal in this particular model, or are we just looking at the errors?
So in this specific case, just the errors. There needs to be, well, yeah, just the errors. Good question.
So you're transforming the data to help the errors then?
Correct. Fix the error normality problem.
Okay, I had one last question, sorry.
No problem.
So earlier on in the slide, it said it used the same prior for constructing both the trees and the leaves. Why is that? Why does it use the same prior? And also related, how informative is this prior?
Good question. So to be honest, I don't know all the answers to that. I'd have to refer you to the paper. The math behind this is pretty complex. And I will be the first to admit that I don't understand how exactly all the math works. But so the prior assumption, do I have it in here, is a normal distribution. As far as I know, there's not much you can do to change that. So I don't know in terms of making that more informative, how flexible the BART machine package is. I mean, in theory, you might be able to make some changes to do that, but you may not be able to use the BART machine package to do it.
So I know from what I read, specifically with BART machine, that the vast majority of the parameters, with all the testing, he just said, just start with the defaults because there's minimal to no change in the performance of the model. So, whether it's the tree depth or the number of leaves or the burn-in for the MCMC, it's all of it. He said just stick with the defaults because, and that I think is partly why the answer to the question. He said we tested across huge grids on huge networks of computers and it didn't make a difference.
Yeah.
So I think that's probably most of the answer is the Bayesian approach converges so quickly that it just doesn't matter.
Great comment. Thank you. Yeah.
And I would just add that I think one of the big benefits of the Bayesian framework is if you don't have a whole lot of data to go from, then that prior can help you say, this is what I think it should be, and so I think it should be influenced to this degree based on how strong you make that prior. So just as kind of an addition to what's been said already, that would be a case when if you've got a lot of data which you probably had access to, it probably wasn't much of a concern because the data could largely speak for itself.
Right. Great.
And again, to boost on what you're saying, the key difference between this and a gradient boosted model is rather than having a point estimate for your learning rate, you're replacing that with a distribution which is so much richer that even in cases of just a few observations, it's just going to learn so much quicker because you have that, all the parameters for that distribution to be able to converge on learning rate much quicker.
Yeah.
Out on that, is there a distribution for each point estimate, like patient
Yes,
X?
for each parameter, for each point estimate,
Yes.
each parameter.
And it's been a while XGBoost even have, or is it just a point estimate?
I don't know.
Good question.
Does
I
anyone
think
know
it
that?
does, but-
I'm not sure that it does.
I don't think it does.
Yeah.
I think you have to,
Bootstraps.
Bootstrap.
yeah, bootstrap it.
No, that's awesome.
Oh, okay.
Yeah. Great. This is great. Yeah.
So I have a question. First model, it didn't look. So for cross-validating, is that inside the BART machine function?
So it's a different.
It's a different
So
function. Okay.
so yes,
And
it would be. I don't know if I
in
have
the
that.
summary, when it gives you your RMSE, your in-train RMSE and all that, does it look different if you use the cross-validation function, or does it give you your training errors and statistics and stuff if it's cross-validated?
Well, so this is going to be on. This was on the test data. So they trained.
Right.
And then they different approaches. So I guess maybe I'm misunderstanding your question.
So if you go to one of those slides, like the one where we were looking at the Shapiro-Wilks,
Okay.
if you use a validation function, does this summary look different, the in-sample statistics?
Yes, it does.
Okay.
It doesn't actually give you this. Just runs
Okay.
through the different, however many folds you specify.
Okay.
And it gives you progress on how it's running those folds. So you want to run it first, just as a regular BART machine, check the assumptions, and then run your cross-validation.
Yeah. Cool.
Do you need JAX or STAN installed, or does this just run out of the box?
So it's the only package that you have to install. It'll install a few other dependencies like R Java and stuff.
As a Java.
Ah, cool.
Yep.
About how long did this take to run? I mean, it's
This-
not a very long MCMC, but
Right.
how long did it take to run?
This ran in about 10 minutes, so it's pretty quick. If you're doing it on, so the data was about 400 observations. Not a super big data set, but if you're running it on 50,000 observations, it would take quite a while. Yeah.
So on that, one thing that I know is really cool about the BART machine is that it's built to be distributable, and it's got that argument for your. So it's just trees like this you can distribute, parallelize super easily.
Right.
How does the parallelization affect the MCMC algorithm with your burning? Do you have to
I'm
burn
guessing
in
it
each
burns
of those
it. I'm sure
individual?
it does. Yeah.
Is there support for any of these parrot or anything yet, like BART or BART machine?
I don't.
It does allow for BART machine implementation. I
BART
haven't done
machine,
it personally, but
yeah.
I'm pretty sure I've seen it out there.
And after you mentioned it, I looked it up. The new package BART does have multinomial support,
Okay.
which is
cool.
cool.
Does it
Yeah.
R Java?
I don't know.
I'm cutting R Java out of my life.
Yeah.
Kinds of functions is BART machine good for? As far as like you said, it's good for predicting outcomes. Are there certain types of questions it's better suited to than others?
Well, I don't know that I can give, I guess, a comprehensive answer to that, but in the healthcare space, anytime that we are interested in predicting length of stay or whether or not a patient will be readmitted or whether they so I guess to give you a few other examples of things we've been looking at, one of the things the patient get an infection when they come to our hospital and provide. And so that would be a apply BART machine in order to predict that. Does that at least a little bit maybe?
Thank you.
It's a good question. Anything else? Yeah.
Kind of along those same lines, are there, when you use BART to answer certain questions, do you usually, is it a small data set, like you were saying 400 was the specific example, do you have a smaller data set, or are there bigger data set questions personally exposed with?
The big that I ever ran through ART was to predict diabetes, and it was 60,000 records, It took about an hour to run that. And it was actually to predict readmission, I should say, in a diabetes population. So no, or not a patient would be readmitted within 30 days if they came in initially with some type of diabetes diagnosis. And that's the biggest data set I've ever ran through. Obviously, you could run something bigger than that. You would just have to be able to allocate appropriate or set up some parallelization to be able to get it to run. But
One other question related, but so just to be clear, the priors they are built package, not necessarily like they're calculated with that right? They're
Right.
not, like there's no input in it if you wanted to change that specific prior.
right, not that I'm aware of. Not in the BART machine.
So you can change the
Can you?
values.
Well, so some of them.
So a couple of ones. You can put a prior which factors actually go in.
Okay.
So the default is that any variable has an equal chance of being selected for a given split. Prior on those, you change the prior on the depth of the tree, so the likelihood of it getting deeper or not. I think the one that they don't really have you touch in the case of classification is kind of the shrinking terminal node parameter.
Oh, okay.
Or the prior on the but I don't think that it has it for those. But for the depth and the variable selection, I'm pretty sure you can do that. I think that's the only two you can influence there.
So some, I guess.
Yeah.
Some flexibility.
The standard variable importance plot.
Yes. Let me see if I can actually show you. I pulled it up here. Oops. Let me just see if I can scroll through it and show you what it looks like. Yeah, so this is variable inclusion proportions, where they show you how many times. That's so small. Let me see if I can make that bigger. How many times something is used in the splitting algorithm. They have to the partial dependence and stuff. Anyway, I would recommend going through this. There's a lot of really good stuff of how to use it. Good example. Any other questions?
So on that note, with that plot, have you ever used BART for variable selection then?
I haven't. I've always put in the variables that we've known we wanted to include.
It's a good question.
Yeah. I don't know if anyone else here has used it for that.
I think it's useful. BART is nice because out of the box you can dump in a whole bunch of stuff and it will kind of give you if you did want to build some sort of maybe more interpretable model, it can give you some good direction on that end as well with some of the functionality that's built in.
Does anyone know that the variable selection, is that almost like a proxy for variable importance, the way XGBoost called it? And is it kind of the same thing?
It looks,
I would say it's fairly similar.
I think XGBoost has 3 different, this one was, number of times it was, XGBoost has like 3 different, I can't remember off the top of my head.
Yeah, yeah.
And there's also,
There's like income node purity.
Yeah,
and
yeah,
Homogeneous
yeah,
as well,
yeah, yeah,
I would guess.
yeah. Nice. Nice. This was super interesting. Thank you. but we'll get that up very soon when we have a date. And you can come and you can keep learning more about these interesting. I think so. We were not able to stream this time, but if you have collaborators or coworkers or friends who are interested in this, we did record it and we're going to upload it. So this will be able to be watched later on our YouTube channel. And please feel free to say hello to us and each other on your way out. And also we've got stickers here if you are a Hex sticker fan, as I am. So thank you so much all for coming.